Welcome back, everybody. So we're going to be looking at section 8.8, improper integrals. So this is also something that we looked at last year during that distance learning portion in the spring. So improper integrals are essentially going to be integrals where we're approaching some form of infinity. So either we have infinite length, meaning the integral itself is approaching infinity, or we have an infinite discontinuity in our function. So let's go ahead and take a look at these. So for the first examples, we've got two different functions, 1 over x squared and 1 over x, but you'll notice both of these functions are very close to each other, right? So 1 over x maybe looks like this, and then 1 over x squared is going to be very similar, but it's going to shrink faster, right? So as x gets larger, x squared is going to get smaller, or is going to get larger faster, which means the ratio of 1 to x is going to get smaller. So we've got these two functions, and we can see that we've got this infinite discontinuity, but we're cutting it off here at 1. So we've got some area underneath, so either this area for 1 over x squared, and then that additional area for 1 over x. So the question is does this area exist? Is it finite or is it infinite? So we're going to use some integration tools to work this out. So if we evaluate this, the way that we're going to do it is actually to apply a limit to the integral. Right, so indefinite integration at infinity doesn't quite make sense. So what we're going to do is we're going to change this to the limit as a value goes to infinity. I'll call it t, of 1 to t of 1 over x squared dx. And we'll do the same thing for b. So we're going to take the limit, not infinity, it is now t of 1 over x dx. All right, so we'll take a look at the first integral here. So that's going to be the limit as t goes to infinity. Our antiderivative is going to be negative 1 over x from 1 to t. And if we want to, we could distribute out the negative sign and flip the limits of integration, but I think I'll just leave it as is. So we'll get the limit as t goes to infinity, and so we're going to have negative 1 over t plus 1, since it'll be minus negative 1. And then we can see as t goes to infinity, right, this value is just going to approach 0. Which means that we end up with an answer of 1. So the area over that underneath the 1 over x squared graph from 1 to infinity is equal to 1. So for b then, if we look at b, we'll do the same thing. So we'll get limit as t goes to infinity. Now our integral is going to be natural log of x from 1 to t. So we'll get the limit as t goes to infinity of the natural log of t minus the natural log of 1 is just 0. So we really just end up with this natural log of t expression. But we know that natural log of t is an increasing function, which means it's going to be approaching infinity. So this limit does not exist, which means that this area does not exist, or what we're going to say is that the integral from 1 to infinity of dx over x diverges. And we'll note for the previous example, the integral from 1 to infinity of dx over x squared converges to 1. All right, so we're going to be approaching 1 without actually quite reaching it numerically. So we're going to have these two competing types of examples where we either get convergence to 1 or divergence towards some form of infinity. So the limit exists as a finite number. We say the improper integral converges, and if it does not exist, then it diverges. Okay. And we'll note here that for both of these examples, these functions have infinite discontinuities, but not on the domain that we're considering, right? So there's vertical asymptotes for both of these graphs at 0, but we're not considering 0. So we've got some definitions here that we're going to use. So if we have the limit, or the integral from a to infinity, then we'll use this limit substituting process for the infinite value. Same thing if it were negative infinity, right? So we can do it for negative infinity as well. A and B are just arbitrary letters that we're choosing. And what we can also do is if we say want to do the entire real line, we can then split our integral into 2 pieces of our choice at some value c in the domain. And then for each one of those, we would use, we would use those given methods above. So even if we have infinite on both ends, we can still apply the same property. Okay. So on the next page, there's a couple of examples, but I think I'm going to jump to our infinite discontinuities example. So we'll note we've got a rational expression with a 4th root, and then we've got secant squared. So let's go ahead and take a look at this. So we've got the integral from 0 to 1 of dx over the 4th root of x. And clearly there's going to be an issue at 0, right? So 0 is going to be the endpoint of that value, but it's also going to be undefined. So we need to rewrite this as well. And then for the secant squared theta, we're going to have a problem at pi over 2. And so if we look here, what we're going to want to do is take the directional limit instead of just the limit as we're approaching the value. So we're going to take the directional limit here. So we can see that the graph of 1 over the 4th root of x is going to look something like that. And so what we're going to have to do is take the limit as we approach 0 from the right. So let's go ahead and do that. So I'm going to take the limit as t approaches 0 from the right, the integral of t to 1, and dx over the 4th root of x, or if you want to, simply write it as x to the negative 1/4 dx. For b, now we're going to be interested in pi over 2, since that's going to be undefined for that cosine value. So we're going to be approaching pi over 2 from the left. So we'll have the limit as t approaches pi over 2 from the left of the integral 0 to t secant squared theta d theta. So on the left-hand side, we'll get the limit as t goes to 0 from the right of the antiderivative is going to be x to the 3/4 times 4/3 from from t to 1. So what we're going to get then is 4/3 times 1 minus 4/3 times 0 to the 3/4. So we end up with 4/3. Whereas if we look at our secant squared integral, we're going to get the limit as t approaches pi over 2 from the left of tangent t minus 0. And tangent as we approach pi over 2 from the left is going to be approaching positive infinity. So again, we're going to get this convergence and divergence. So A is going to converge to 4/3, and B is going to diverge to infinity. And again, what we're describing here, if we're looking at, say, A, is that region that we're considering from 0 to 1, meaning no matter how close we get to 0, right, we're going to have this infinite length that we're adding, and it's always going to be approaching 4/3. So it'll be something slightly smaller than 4/3, which is pretty amazing, all right, given that it's infinite length. Whereas for 0 to pi over 2 of our secant squared graph, this area is going to continue to get larger and larger and larger no matter what. It'll just continue to increase in size. So there's something about how much your area shrinks, how fast. And this will be something that'll be really important later on when we discuss sequences and series. And we'll use this integral test of convergence to determine some of those summations. Okay. So that really covers the two types of improper integrals we're going to look at. One's with infinite discontinuities and one's approaching infinity. So I think I'll stop the video here and then we'll come back next time and start working on examples. So again, shoot me an email or come by the office hours if you have questions. Otherwise, until next time.